Hey, good morning. All right, so a couple quick things. So we got the exam stuff taken care of. Everybody's grade and response should be available on Sakai. We managed to recover all of the actual submissions. So I went on this whole spiel on Wednesday about check your code and test everything thoroughly. And Sakai unfortunately decided to say, hey, let me drive that point home. So they did a huge update on Wednesday, the day before the exam. I think everybody got an email about it, and it had a lot of impacts on how things were being saved. And for those of you who tried submitting the exam right at the end, you all remember we had a huge group of people right in the back trying to figure out what happened. So to give you a quick summary of what I did after I did my data structures lecture, I called up OIT, let them know there was an issue, let them know it was a big issue, and I asked them to put it as a priority. And it got to the point where we were talking to people up at corporate. And at one point, somebody at corporate thought they had inadvertently deleted all of the exams and all the responses. And I don't think I have sprinted. I sprinted over to OIT. I don't think I've run that fast since I was in the Navy. It's been a long time. So eventually, after about 5 hours of troubleshooting, we managed to recover every single mark that had put in there. And what we ended up doing is we went through, and if there had been 2 submissions, especially for those of you towards the end, we went through individually. And if you had one submission with the wrong answer and one submission with the right answer, the right answer was the one that you found that was put into the system. There was one submission that with an answer and one submission that didn't have an answer, we put the answer so you can at least get partial credit. So that's how we were able to cobble everything together, and we managed to recover every single submission, which is nice. And I apologize for the amount of stress because I kind of was hoping to post everything at 1, and I wasn't able to get up until about 7:30. As for your performance, 87.5% median. Outstanding work. That was a big job. Pat yourself on the back. It's really good. Really, I wouldn't extremely happy with how that went. So keep up the good work. We're going to start getting into this idea of reading in information. We worked on it a little bit. We did a little bit of F-scan-F, and we learned a lot about gets last week and why it is that gets is bad. And part of the reason why I did this review of why gets was bad last week is because it was a really good review of everything that you learned about pointers and memory allocation and how things are allocated on the stack and the heap. So if you understand why it is that gets is no longer used in the C-STAN 2011 standard, we saw over and over again, please don't use this, it's bad, and we learned about stack smashing. If you understood that, then I felt confident about how you're going to go into the exam. So now what we're going to do is we're going to learn the good stuff. How can we read in from files? How can we read in information and use that in a program? So, come on, you know you want to. There we go. All right, so being able to read in from a file at runtime. So I want you to think of a file in a computer as a character array that gets to stay there after you're done. So we've allocated a character array. We use mouth, right? Or we can use quotations, or we can do all kinds of different things. And once the program is done, the character, we either free it, or if we use this in garbage collection, it frees the memory, and it's no longer there. For a file, what we're going to see is that a file can be there when we start the program, and a file can remain there after we complete the program. So the other thing is we're going to learn about reading, writing, and appending. So in reading, we're just going to go in, we're going to get the information, we're going to read from the file. For writing, we're actually going to write to the file. And if we're just writing, that means we start at the base address of the character array and overwrite everything that was previously there. If we're appending, what we're going to do is we're just going to keep writing afterwards. So we have to save some sort of information to indicate that we still have our base pointer for the file, and then after that, we would be able to write on afterwards. So that way we wouldn't lose information in the file if we want to append to it. All right, so couple quick, we're going to go over these three functions in detail today. You'll see in the lecture review that my questions focus on understanding the difference between these three functions. So getC stands for get character. And you read in some sort of file stream, and it scans the next ASCII value. So for those of you who've taken C before, you're probably familiar with the function printf, right? And you may have noticed that as I've been coding, I've been using fprintf, right? So in fprintf, you had to do this standard output. So the reason I choose to do that in a fundamental programming class is because it helps give the student the idea that there is something coming in or something going out, and it's not just magic that you actually have to send it somewhere. So when we do fscanf, that means we are getting a file pointer, and then we're scanning from it. Same thing with fgets. We are getting a string from a file. Now, fgets, what you're going to see is that in 2011, they fixed all the issue with gets, and now they use fgets as a secure way to read in a specific string. So it's permitted, yes? Good question. So gets was actually part of the original C programming language all the way back in 1972. Yes. Yes. Welcome to bureaucracy. It's like the DMV. So any other follow-up questions? Did I address your question? Okay, cool. Any other questions? Okay, so fscanf, we scan in the input from the user into an address of a variable. So if you remember, when we first worked on this fscanf, part of it was to enforce this idea that we're passing an address to a function. And the reason why we pass the address to the function is so that we can pass it by reference. So the only we needed was a pointer, and we could do something simple like an integer, but as we're building up more information, for example, a string. I only need a pointer to the string, and then I can have several values. Likewise, now I'm reading in several even larger pieces of information, and then that's where this pass by reference comes and benefits us, because now we're only taking in one 64-bit register instead of having to make an entire copy of the memory. And as your programs get bigger and bigger, this is going to be something that's more and more beneficial. Just a brief aside, so in the data structures course that I'm teaching them about graphs. And graphs are huge data structures that have dynamic arrays upon hash tables, upon queues, upon stacks. And instead of having to make a giant copy of all that information every recursive call, all you have to do is pass by reference to get that graph. So it saves literally millions of bytes in order to implement the graph. But here, as on a more fundamental aspect of it, all we're really worried about is getting in and getting out and being able to get pieces of information that we can operate on. So standard in is reading in from the terminal. You've done this a little bit already. So standard in, that means you're typing in to PuTTY, and that read and set information from the keyboard, and that allows you to put in real-time input. File pointer, and it's important to know before we go any further, file must be in all caps. File, right? Very loud. I am a file. The file pointer creates a location in memory where you would be able to store a file. And then treats a file like a data memory. And then the crucial part is we understand this idea of ASCII value. And it has all these ASCII values. And what we're going to learn later in this lecture is that a file terminates just like a string was doing in the last lecture. So does everyone remember how we terminated a string? Yes. Yeah, /0. So we ended it with null, right? So there's, we can either say null in all caps, we can say /0, or we can say ASCII 0. Those are all synonymous. So yeah, that's exactly how we do it. So we do it the same way with a file pointer. Yep. That computer didn't want me to lecture today, I guess. All right, so first function I want to show you from the file library is file open. So with open, we see const char file name. So const, as a review, is our way of saying that you pass something to a function that cannot be changed. So here, I'm reading in a string, and then I indicate how it is that I want to access it. So for example, here I have a file name.txt, and then in quotes, I have R. And so that means I want to define this function, this file, as read only. I just want to read from it. So that should say fopen. We have fopen there, and you put in the file name, and you do that. So you read in, and you also read in a mode. Okay. So the three major types of modes that we're going to use in this class are read, write, and append. So read means that we are only going to read from this file. So in a way, you can think of it like a const character array. You're not going to be able to manipulate it, but that's okay in many applications. Often I just want to read from it and be able to get pieces of information. I don't need to write to it. I don't want to mess with it. I don't want to give the user the ability to mess with it. So if you're writing a function that returns a file pointer, they can put in the file name, and you can say, all right, I'm going to call fopen, but I'm going to limit it such that you can only read from it. So it provides a level of security. The next one, W, is write. So write is specific in that you have a file pointer that points to that location, and you immediately define that file as empty, no matter what was in the file before. When you do W, you're saying, all right, at that pointer, I'm going to start putting in characters. And I'm going to allocate memory as we're writing more information into the file. The drawback of this is that if you want to save your information, W is not the right way to go about it. If you put in W, anything that you saved had from before is gone. Which is why, if you want to save it and you just want to write afterwards, you can use A for append. So append means that I want to write to the file, but I want to ensure that anything that I have done before is still there. So basically, when you write, file pointer is always pointing to the base address of the character array. But append is basically saying, all right, that's all well good, but I'm going to do some pointer arithmetic. I'm going to cast a file pointer to a void pointer, and then I'm going to take the file pointer, I'm going to cast it here, I'm going to add the current size, and then I'm going to start writing stuff afterwards. So just like we did initially, right? We did that with string concatenate. But now we can do the same thing with files. So closing the files. This is, you're going to see me hit on this point over and over today in today's lecture. When you're working on closing a file is very much like we use free when we allocated memory. And so there are some issues with this. If we freed memory we didn't allocate, we got a segmentation fault, right? And if we freed memory twice, we got that huge memory map. And the reason why we got the memory map is because the operating system was like, wait a minute, I know I had it. It's like it's checking its pockets. I could have sworn I had it, but then you left your keys back on the table before you left the room. It's the same way with the computer. I know I had this memory allocated. I'm trying to find it, except it's unable to. So when you do fclose, it's the same way as doing free on the character pointer, but if there's no file with the file name, it will be null, and it will result in a segmentation fault. And so what I always do, this is a rule that I apply whenever I use file, is I say if a file pointer is null, then it has some sort of case, and then I'll do else, and I'll do all the work with the file in that else statement, and at the end of that else statement, that will be where my fclose function call is. So I do that as a level of security. You'll see that in an example in code. Okay. Does anybody have any questions before I continue? Yes.
So when you're writing a file, let's say the file is a sentence.
Mm-hmm.
The first word is like 5 letters. You write another. If you wanted to write to the file, and you wrote like a 5-letter word at the pointer at the beginning of the file. Mm-hmm. Would it clear the whole sentence, or would it just overwrite the first?
If you use W, yeah, we'll clear it all out and start over. If you use A, then we'll have 10 characters. Any other questions? Okay, so the first thing I want to do is I want to show you an example of bad file pointer allocation. So I'm going to go through this whole thing. And in my directory, I have a file called int file, but file DNE stands for file does not exist. And so I create 2 characters, character arrays, and then I call fopen twice. And I set them both equal to read. So file pointer 1 and file pointer DNE. And it's going to return the location in the computer where that file is located. So file pointer 1 is going to be there. File pointer 2 is going to return null because I don't have a file with that name. And so before I do that, I should point out that standard IO, as we've done in the past, is going to contain all those functions. So here's the right way to do it. I'll say if file pointer 1, which exists, is equal to null, then I'll print out a statement, the file does not exist, and exit -1. So exit -1 is like return -1, where basically we terminate the program. And if we send -1 to the operating system, we're indicating to the operating system that the program did not complete as we anticipated. Else, in the event that it wasn't null, what I'm just going to do is I'm just going to close it. That means I'm closing access to that file. It doesn't mean the file is gone or deleted or deallocated. All it means is that we're not writing to that file anymore. So the second part is where I do things wrong. So here, if it's equal to null, I'm going to print it out, but notice that I don't terminate the program. And then after that, you're going to see that I'm going to try to close a null file. Does everybody see how that code is run? So let me show you, make file pointer example bad. Right, so we compile it, and we see that we have an int file .text, but we don't have the other file. So we'd say file pointer example bad, and we'll see that it's segfaults, just as we anticipated. So far, we know that this is not going to work, but let me ask you this question. So what if I replace fpDNE with fp1? So this is the file pointer that we allocated, we checked for it, it was there, and we closed it. What do you think is going to happen when I run this code? Yes? Okay, so that was the crucial thing. So it's already cleared out. So let me run this. So it compiles, and it gives us a completely different thing, but we've seen this before. Double free or corruption, right? Have I all told you the story about my classmate who got so mad at this error? Like when I was a student back in the year. I haven't told you all that story? Okay, so we were working on file pointers just like you all are right now, and my friend Matt Dowski, he was trying to figure out what was going on with this, and he must have spent like 10 hours trying to troubleshoot this error. And so I come in, I show him, hey, it means double free. And we looked at his code, it's like, hey, you're free to file twice. And what ends up happening is it's just trying to look for, because it's still in the operating system saying, hey, somewhere I had this thing, I'm trying to find it again. I must be losing my mind. Why are you asking for it twice? And he got so mad, he threw his water bottle and broke one of the windows in the lab. He spent 10 hours on this. So the moral of the story is, this is why I always say, read what the compiler error states. Because sometimes it's not entirely clear, but I promise you that we are trying to convey to you why the code is wrong. So here it said double free, so in this case we're freeing it twice. But if I go back to the other code, and I did fpdne, the reason why this only seg faults instead of doing this memory map is because we never had it in the first place. So that other trace is like, I swear I had it, but this time I never had it. This is just a seg fault. That's bad news. Okay, does everybody see the difference between those two? All right. Okay, so proper file. So this file has a minor just modification. So the only thing that's different between this file and the previous file is that here, in this last portion, I say, well, if it's equal to null, I say it doesn't exist, and then I exit -1. So now I'm going to run make file pointer example, and I run it, and it says the file dne.txt does not exist. Closes clean. You have a segmentation fault, did not have a memory map trace. So that else case that I did is there is an extra level of security to ensure that we're not trying to access memory that we don't have access to. Does everybody see how I did that and why? All right, so before I move to me, okay, no questions in the chat either. Okay, so what exactly is a file? This kind of gets back to your question I asked a little earlier. So when we type into a file, we are putting in some sort of information. So this goes all the way back to the beginning of the semester when I went over this idea of a Turing machine, right? The Turing machine is you have one person outside the box who speaks in some sort of language, and we input a bunch of information, and then there's a person in the box who has a book, and they're translating these bits into operations to do, and then they put the tape back out, and then the person on the output is reading it and seeing what that actually means. So files are a really good example of why it's important to understand this. Because on the left, I just have 10, 137.4, 22 Notre Dame, right? And me, with my brain computer, and you with your brain computer, see that and understand these are numbers. You say, oh, that's an integer, that's a float, and then I have a number, and then I have 2 words. So what's actually going on with the computer? Well, the computer, now we're getting a little closer. What is actually going on here? So I have ASCII values, and then 10, ASCII value of 1 is 49, the ASCII value of 0 is 48, and then I have an ASCII value of 10, which is a new line here, right? So that means that's how I'm creating the new line, and you'll see the same thing, 137.4 new line, and then 22, you'll see 50, 50, and then all of the ASCII values for Notre Dame, and then the new line character for 10, and then you'll see -1 at the end. But here's the thing, it's all memory. Remember, long unsigned integer. It's all just one big chunk of memory that we tell it what to do. So what a file actually is a long set of values of ASCII in a straight line. So what we see versus what the computer sees. And that's why we say this idea of a computing tape. And then nowadays we use memory. So memory is just a big long chunk, and that's what we can do and put it into whatever we want. So now there's several ways we can access this information. If we have fgetC, what this means is go to the file pointer and get a character. And we see that we have all these ASCII values, so we can actually get a character and read it in. So we want to read the next character from the file pointer. And so if we're reading from standard in, we're just getting the next character from the user and performing some sort of operation on it. If we use a file pointer, that means we are just getting some sort of information from a file and operating on it. Now, I want to talk about these advantages and disadvantages, because these are really important and when you're kind of deciding what it is that you want to use to read in from a file. So for fgetC, there may be a specific reason why you need to check every single input. So for example, let's say that you want to write a function and you must absolutely be certain that what you're reading in is a float or a double, right? So what do we need to know about that? I need to know that I'm allowed to have negative numbers. I may have a decimal point, but I may have at most one decimal point. And they can also be represented by E to have some sort of power. So I would have to write a function that would go in and evaluate each character to make sure that it is in fact in the proper format. So if you need something that has complete control where you're evaluating everything, fgetC is a really good function to use. However, and this is the crucial part, you need to know what the terminal condition is. So you either need to know when it stops it. Now there's a keyword I'm going to show you in a moment, EOF, which stands for end of file. Which is also just looking for the ASCII value at the end. And furthermore, the more you have to break it down in modularity, the more complicated it can be to code. So for fgetC, there's actually a really useful tool to help simplify things. And this is, you start using your idea of this while loops to be able to read through every single element in the file. So normally, when we have some sort of while loop, we just say while A does not equal B, and then I perform some sort of task inside the while loop, right? However, I can start doing crazy stuff like this. I can do several tasks in one line of code. The question is, what is this jibble jabber? And how is this actually going to help me? So first, let's break this down piece by piece, okay? First, we just have this temp char inside, right? Temp char equals fgetC fp1. So fp1 is what we're calling our file pointer. And we pass the file pointer to fgetC, and this returns temp char. So now we have defined a character variable and replace it. So that's just this is how we would set this. And once we do that, well, now we can take that temp char and we can compare it. Temp char does not equal end of file. And it compares that character to the end of the file, right? And then we keep doing a while loop, which means we'll just keep going until we get to the end of the file. End of file is a reserved keyword for the integer value -1. So let me go back here, and now let's break this full piece of code down piece by piece. Temp char equals fgetC fp1. So file pointer, which is pointing to a location in memory, and it gets the next character and saves it as temp char 1. Then I compare temp char 1 to my termination case, in this case, end of file. And it's going to keep doing this until I get to the end. So every time I pass file pointer 1, it's going to move it to the next character. So remember I had this whole thing about we have to point to the base address of the character, but we also use this reference pointer to get the next location. fgetC is doing that for us. All right, so let me look at file pointer print. And this piece of code has the same thing. I have an error check. Now I'm going to read, I'm actually going to type in a file name from the command line. And here's what's going to happen. From the command line, I have int argc and char star star argv. And the argv0 is going to be the executable. That's going to be file pointer print. And argv1 is going to be the name of the file I'm going to put in. So I'm now going to pass that character array, and I'm going to read it. And we're going to define that as file pointer fp1. From there, I'm going to do the same check as I've done before. If it's not there, it doesn't exist, we're going to close the program. Otherwise, now I'm going to say that the file name was found. And so I do file %s, and then I use argv1, so we're going to say the actual name of the file is there. And then, remember how I said I wanted temp char? But I have int, right? Just a friendly reminder that characters are just nothing more than integer values in 8-bit form. So this is code that will work. If I put in char, that would work just fine as well. And I will say that the ASCII value is %d. So it's going to print out the ASCII value. The other way I could do this is I could say char, temp char, and then I could still have %d, but then I would cast temp char to int. So both are valid approaches. And then notice how fclose again is in the else statement. So I'm preserving and I'm not allowing us to access or close a file that we don't have access to. So first thing I would like to do is make file pointer print. And then first I'm going to do it with no second input. And you'll see that my error checking catches that. And then I'm going to say file not here dot text. And again, we have it right. And then I just want to make sure it is int file. Okay, so we're now going to say int file dot text. And here now it's printing out all the ASCII values from the file. And then it says ASCII value is -1, so we know that we have terminated file. And then I think the other one is sample.txt. In sample.txt, you'll recognize this. We have the two 50s in a row. Sample.txt contains the exact information from the slide. So this is identical. Now we've seen precisely what's going on in memory. All right, does anybody have any questions about that before I continue? Yes. Sure, so we aren't doing that, right? But it's doing the work for us underneath. So for a file pointer, it has two files, two pointers, excuse me. And so it's kind of doing the exact same thing that you did in the Haiku assignment, right? So you created a pointer and then you created another one to increment down. It's doing that all underneath the hood for us. So it keeps track of where the file pointer begins as well as which character we most recently accessed. So it does all that work underneath. There's a question. Awesome. Yes.
So is that
End of file. Yes, it is equivalent. Very good. Okay, so let me, I'll show you. It terminates when we reach -1. So EOF is a keyword that means -1 in the CUF. Yes. So ASCII values, when you have a character, ASCII goes from 0 to 127. However, a character goes from negative 128 through 127. So if it's a signed character, and an unsigned character can go from 0 to 255. So what's going on here is when you read in the character, it's reserving -1 as a specific ASCII value to terminate a file. Yep. Does that just run? Yeah, standard IO. Yes, standard IO includes that. So it's anything with input, output, and it's a file, so it's standard IO. Right. Any other questions? All right, let's continue. Okay, so there's the same thing. There's the output. You see that it will match precisely what we anticipated when we created the animation before. So fscanf. So you're familiar with fscanf already. You used it briefly, and used briefly to read in from the command line. So fscanf, when you used it, your file pointer was standard in, since you're reading from the command line. But now we're going to get it from a file. That's the exact same idea, and what's going to happen is I am going to pass a string, so let me show you here. If I go to file pointer fscanf, I'm going to do the same thing. I'm going to read in a string into temp string. And so what's going to happen here is it's going to say, all right, I'm going to read every character between here and when I encounter a space or a new line. So space is 32, new line is 10. And so I'm going to break it into pieces and print it out that way. And so the difference is now I'm going to interpret it the way it's written in the file. So before we had ASCII values, and that's how the computer is doing it. And now we have the string approach that's saying, all right, now I'm going to pass it by reference. And remember, whenever we pass a character pointer, we're going to call this by reference. And so now we're going to print out the result. And so, but before I do that, there's one thing I want to point out. There's a flaw to fscanf. fscanf can only print out up to 200, can only read in up to 256 characters. If you try reading in more than 256 characters, we're going to run into some problems. And also I'm going to show you how to get around those problems a little later. But just like before, it's going to read through, and if it gets to -1 at the end, it will terminate the file. So gets to a space, gets to a new line character, gets to end of file. Anything else, we're going to put it together as strings. All right, does anybody have any questions before I continue? In the chat. All right, so in this file, just like before, I've done all the tests. We're reading in from the command line, and then file was found. Long on since signed in malloc is 256, and then I'm going to read in from the files, and the string contains the previous value after end of file. Basically, what that's saying is at the end of the file, I have this last string, and each time you'll see that at the end, I'm going to free temp string, and then I'm going to close the file. I'm doing it inside the else statement, so that way I can ensure that I'm not having any memory issues. And so we'll see here that I have several files, but at the end I'm going to put in more than 256.txt. So let's do make file pointer fscanf. It's going to compile. And the first thing I'm going to do is I'm going to read in sample.txt. And now when we put it out, we'll see that's 10, 137.4, 22 noter and dame. And then if I do int file, you'll see that I have a number of integers in there. So it's putting those like so. So now when I do more than 256, what's going to happen is it's one huge string that's significantly longer than the amount of memory that I've allocated to the array. And so now we get one of these memory maps again. So I read in this string, I have this, and now it's the reason why this is happening is now it's trying to free and reallocate memory again in the same call. And it's not going to like it. And so this kind of gets back to the question that you were asking earlier, that we're using this file pointer and we're allocating memory. But the thing it doesn't like is now we're trying to do double free. And so that's why it didn't work. So you have to make sure that the amount of memory that you allocate for fscanf is the appropriate size. All right, does anybody have any questions? Okay, so how do we get around this? So let's do some editing. So fscanf edit here, done the same thing, but now what I'm doing is I have this case where I'm reading in fgetC, and I'm reading in the total size of the string. So what I'm doing is I'm going through the file, right? And I'm reading in everything and I'm getting the total size. And then what I do is I close the file and then I reopen it to the same location. And so now what I've done is I'm now back at the beginning of the file. Does everybody see that? And then what I'm going to do is instead of using 256, I'm going to allocate it to the size that we actually know is in there. And so now that will have the exact string size that we need in order to be able to get the information. And then you'll see I'm doing the fscanf file pointer %s temp string, just like we did before. And because it's a character pointer, we don't have to put the ampersand in front of it, because by definition, when we do a character pointer, we are already passing the address. And so let me run clear make fscanf edit. And then if I run this, we'll see that I have int file.txt, sample.txt, and then if I have more than 256.txt, now it reads in the whole thing. So the reason why it worked like we did before is because it loops every time we get to a space or a new line, whereas here, there's only one termination, and we now know precisely how many characters are in the file, therefore we've done so without having any seg issues. Okay, does anybody have any questions? All right, so fgets. So now we take in a file character to allocate to the user. It's just like fscanf, except it also returns the character pointer as well. So what I wanted, I'll leave it there a quick second so everybody can take it down. So the difference here is it's now returning the character pointer as we're reading in information. So what's going to happen is with fgets is that it's specifically designed to get around this issue of stack smashing that came up with gets originally. So here's what's going to happen. You allocate 256 bits to this particular string, and then you try to put in a string that goes over 256. It's going to say, that's the end of your string. Let's go to the while loop and read in that element to the next string. Does that make sense? So whenever I call file pointer fgets, the major difference is it's the same thing, but now I'm saying temp string is equal to temp string. I have malloc size, which I've done is 256, and file pointer 1. And in more than 256, of course, it's more than 256. So we're going to see that it's going to become 2 strings. And we see that we have the initial string here. That was at the end of 256. And now we see that it reads in the rest of it into a new string. We see that the ASCII value at the end is null because we've read in the end of file. All right, so file out, let's say we want to write, right? We want to write stuff to the output. So file pointer, instead of doing R for read, now we're going to do W for write. And now if we want to write to a file, all we have to do is use this same fprintf function that we've been using all semester. Except instead of standard out, now we just call it the file name. So here in this particular slide, it's fout. And what we're going to be able to see is that we're going to print stuff to this output. Hey, does anybody have any questions? All right, so here in this file, fprintf, what we're going to see here is that I have opened it with a W, and then file was found, and then I want to say hello world from %s. So I'm going to read in argv1 just like we've done in previous files. I'm just going to name the output file that I want to create, and we're going to see that it's going to create a file with that element in it. And that's the only difference here. So we're going to see that I do not have a file called output.txt. So I'm going to create a file called fprintf, make fprintf. And then if I run fprintf, and I'm going to call it output.txt, it just says file output.txt was found. But if I press ls, you're going to see that we have an output.txt file now. And if I type vim output.txt, we'll see that says hello world from output.txt. So instead of printing it just to the output, we can print it to save our results. And so the last thing I want to show you before we dismiss is what if I want to read in from a file with different elements or different types? Well, this is where I can use that fscanf function. So now I'm going to create a file pointer, but now I can read in multiple elements at the same time. So here I have a piece of code, and we see I have fscanf file pointer, and then I have %d%d. And this allows me, now that I'm going to pass the address of height and the address of width, what this function will do is it will read in from the file and then store the values at that location as integers to height and width. Does that make sense? So what I want to show you is this multiple.c, and here what I've done is I've created 2 integers, height and width, and then I use this fscanf function, just like I showed you, and then while I have information in there, it's going to print out those values to the user. So you see height %d, width %d, and then area I just multiply them together here. So what I'm going to do is I'm going to run make multiple. And then the file I'm going to write in is multiple.txt. And then I have 4 elements in there. So the file, if I look at it, multiple.txt, will say 10, 20, 30, 20, 15, 10, and 5 and 20. And so fscanf is able to determine these as integers. So then what I do is I read in, and now I'm printing them out. So now I can use this as a way to store information for which to perform operations on. Here's how I want to conclude today's lecture. The benefit of this is as we start to really start building into bigger projects, right, and especially as you start doing this in your career, you can create multiple files that you can use to test your code. So you're like, I know that this test will work, I know this test will work, I know this test will work, and I know what I expect the output to be. So what you can do is you can have an input file, you can have an output file. And then you run your code, you run those through the executable each time on the different test files, and then you have output results. So that way you can prove to me, the TAs, or to your boss, whatever happens later on, that I came up with these tests on my own, and here's the proof that I ran it, and here's the output. Does that make sense? This is where we can benefit as we really start moving on into higher level types of computational thinking. So on that note, it is 10 o'clock. If nobody has any questions, you are dismissed.